Hello, my name is Konstantinos Karaidis, and I'm excited to give a short overview of our recent agricultural robotics and automation work that has appeared in IEEE RAM, and it is also presented as part of ICRA 2024. This work is collaborative between two University of California campuses, UC Riverside and UC Merced. From a general point of view, physical sampling and follow analysis of different plant specimens is most often the single most accurate way that we can measure different parameters that are important to determine plant status and its need for watering. These processes can in general be quite laborious, and this is at the same time that agricultural workforce is shrinking. Because of these reasons, typically there is very sparse sampling, both spatially and temporally. Agricultural robotics and agricultural automation technology can help serve as a means to mitigate these challenges. While these are quite general and can apply in different types of crops for different types of applications, this specific work focuses on stem water potential analysis. Stem water potential is a very important metric that helps determine how to schedule irrigation and assess their efficacy. Let me give a little bit of an overview on stem water potential analysis. The main operating principle is as follows. There is a person that goes into the field around noontime. They are putting a bag around a leaf. They let the leaf there for about 10 minutes and then they cut it very carefully at its stem, and then they take the leaf, they put it inside the pressure chamber, they secure it, and then the pressure is increasing inside the chamber. When the pressure reaches a specific point, then water will start coming outside of the exposed part of the stem of the leaf, and then this pressure is being then noted down, and through already known information, it can be linked to plant status or its stress. Typically, to do this, in the figure at the bottom left that you see here, a person has to look through a magnifying glass and then slowly increase the pressure while at the same time being extremely careful to determine when water comes out. And many times this process has essentially different readings depending on how different people might actually perceive this. The proposed approach that we're following here is that we have a robot that determines which trees to sample from. It retrieves a leaf, it gives it to a user in some station that it is this stem water potential analysis station, and then the user places this leaf inside the pressure chamber, and then that pressure chamber essentially takes over and does this whole stem water potential analysis on its own. So not all of these components are essentially amenable to automation. So for instance, bagging a leaf, this is a process that can be quite hard for a robot to do, but a person can do it quite easily. However, those components that we have essentially focused on here are prone for automation, and we saw in this work how we can do this. In sum, the contributions of this work are threefold. First, we perform informed path planning that considers motion energy constraints to determine where to sample. Then we perform component selection and overall system integration for an agricultural robot performing mobile manipulation into the field. And further, we develop visual learning methodologies that can help automate the single most labor-intensive process within stem water potential analysis, which is to determine the point that xylem water is essentially, or when the stem becomes from dry wet, and this is what we call the xylem water expression. In terms of informed path planning, the goal is to select which trees to sample leaves from. The approach we are following here is to use Gaussian processes that can help dynamically assess the trees that should be sampled next, given a current measurement that we have made. And then, once we have this information, we pick a tree to sample next, based on optimizing a cost that considers the motion energy of the robot. So essentially, we want to maximize operation while sampling the most informative locations. In a summary of our findings, on the left-hand side you see the ground truth. If you have multiple sampling points that are essentially, because it's ground truth, sampled at the most informative locations, then you can see the information map on the right-hand side. If then we sample points given a small energy budget, and then we also plot the paths to go from one point to another, here we're using RRTs to be able to essentially go from one point to another, although any other methodology for planning would be applicable. So with a small energy budget, you can see that the two main hotspots from our information gradient as shown in ground truth, we can essentially capture it. And then if we do the same process with a large energy budget, then we can essentially reconstruct that underlying information gradient quite accurately. In terms of robot design and deployment, the goal here is to perform autonomous leaf retrieval with a mobile manipulator. Our approach encompasses three main steps. The first one is to do component selection and system integration, and importantly, we want to do something that works both indoors in in-lab settings as well outdoor in field settings. Second, we need to co-design the actuation and perception components for that mobile manipulator. Our mobile manipulator is equipped with a custom leaf cutting end-effector, and we want the robot to be able to detect, localize different leaves, estimate its 6 depots, and then based on this information, plan the motion of the arm so that the end-effector will get close and then encapsulate the leaf, and then we'll cut it, hold it, and retrieve it. And finally, we want to deploy this and assess how this is being deployed in both static and dynamic settings. Our main findings here show that we can improve based on earlier results by essentially doing a more careful component selection. For example, cameras that we're using for visual surveying, the different type of motor selections to be able to cut different leaves cleanly at the stems from different species. Here we have considered so far avocados and oranges that we are showing results about, but in this initial process we also consider different species, mostly other types of citrus and almonds. And finally, we also perform a complete system integration in field deployment. We are using multiple sensors for both autonomous navigation and scene understanding. For autonomous navigation, we are using data that come from wheel odometry, IMU, and GNSS positioning, and we're also using LiDAR data, both to construct local maps and to perform scene reconstruction, whereas a camera that is mounted on the end-effector is used for localized information gathering to detect leaves and guide arm manipulation. We perform multiple experiments in the field under variable ambient light and wind conditions. At the interest of time, I'm not playing back the video here, but the link is shown below, so I would encourage you to watch that video and see how variable conditions we can actually get into the field. The last component of this work focuses on visual perception and learning, and the goal is to provide an automated way to detect xylem water expression. Our approach is first to collect leaves from different species. So far we have considered avocado and citrus, and then perform manual stem water potential analysis. We use two commercially available chambers, a portable one which is like a bike pump and a static one which is like a suitcase that you'll put on top of a desk and perform the analysis. We collect the video footage, we manually annotated the dry or wet xylem status, and then we train classifiers. Our main findings show that the YOLO classifier, different variants of it, work essentially pretty well. V5 model is a little bit better because it can work as equally as V7, but it can also be deployed on edge computing devices, whereas lighting variation and motion effects can give us some false positives and false negatives or no detection at all. To sum up, our work is providing encouraging results toward automating the stem water potential analysis and certain processes associated with it. Certain limitations remain, for example, improving the classification and detection accuracy, in making improvements into the hardware design, and making the whole system completely autonomous. All of these are part of our ongoing work, which we expect to resolve in the near future. With that, I would like to thank you for your attention, and please reach out if you have any questions.